Then guys, right, we've done a number of videos now looking to deduce the rate equation from experimental data. We've looked at calculating the rate constant k from taking a line of that data, and we've looked at calculating the units of k. So big E type questions. Now I'm sort of looking at how the examiners can faff around with that and go from different directions, and you need to get your depth of understanding much greater than just being able to do that, although that's probably 60% of the topic. But as always, they can ask some quite nasty questions. So what I've done is put together some things that they can hit you with in the exam. So this one, I suppose you could say, it's called rates numeracy practice, and I suppose what we're trying to address is how changing the concentration of a reactant affects the rate. Okay, now you'll be given the rate equation. So the rate equation, you don't have to deduce it, you'll be given it. So it's a different way of looking at it. You've got a rate constant K, you've got two substances, hydrogen peroxide and iodide ions. Okay, those two, and for hydrogen peroxide and iodide ions, okay, that's what's in the rate equation. Now, the overall equation I will give you, okay? The overall equation for this reaction is acid, which interestingly isn't in the rate equation. That tells you something, okay? Plus hydrogen peroxide plus iodide, two of them, makes, there's your iodine in solution. Aqueous, aqueous, aqueous. You've got to be aqueous, otherwise you can't faff around with the concentration on these. Okay, now iodine is going to be a colour used using a colorimeter to continuously monitor the progress of the reaction, hence calculate the rate from the initial rate always. Okay, so there's your visual side of it. And water. Okay, now as an aside and totally separate from what I'm doing now, do the redox for that. Do the redox half equations. Hydrogen peroxide's a bit weird. Okay, hydrogen peroxide, you need to get your head around. Let's do the. So you should stop the video and you should look at what I'm doing. That's a redox reaction. Good practice. So you do the easy bit first. Ox. Right? Hydrogen peroxide. Now, peroxide, normally oxide. Oxygen has an oxidation state as an oxide of 2 minus, -2. Peroxide is a special case, okay, and it is when the oxidation state of oxygen is -1. And peroxide, because actually oxygen doesn't like to be in the peroxide -1 oxidation state, often it changes to water where it's -2, where it's just the oxide. So peroxide is quite heavily involved in a lot of redox reactions because it readily does this. Here is the peroxide ion. If you work this out, you will find that it's O minus, certainly is, -1 there, okay? And it becomes 2 minus in water, the normal oxide ion, O2 minus. So, in other words, two of those, plus 2 electrons, reduction. That's the half equation for peroxide. Okay, so you've got a straight redox there, no problem. Okay, do that yourself, suss out what's going on. Hydrogen peroxide, they like it. You sort of meet it as you gradually go on. Anyway, I don't want to get bogged down in that. Okay, there's the rate equation. That's what matters. That's the overall equation. Fine. All right, so here's the rate equation data. Okay, so hydrogen peroxide, concentration, iodide, concentration, always moles, dm cubed, moles, dm cubed. Okay. I'll put this in. It's a reactant. In a way, I'm sort of going backwards in a way, but it'll all come clear. Rate. So you're provided with this data, which should match the rate, which will produce the rate equation. Okay, but got the rate equation. Where are we going? Moles, dm to minus 3, moles, dm to the minus 3 per second, units of rate. Right, hydrogen peroxide. Start off with the concentration of that 0.1. Start off, looking at the wrong one. Start off with 0.02. Start off with a concentration of iodide, 0.01. We start off with a concentration of H plus, 0.005. Okay, the rate is given 2.3 times 10 to the minus 6. Right, then they're asking you this. Okay, look at the next line. We double the concentration of this to 0.04. Okay, we keep the concentration of this the same. Okay, and we keep the concentration of this the same. The question is, fill that box in. That's the question. Okay, what do you think is going to be the effect on the rate? So stop the video and have a go at deducing that before I tell you. All right. Anyway, double this. What order is it? First order. You double the concentration of that, you double the rate. Simple as. So I would expect the rate to become double that, first order, double the rate. Okay? That's worth a mark. That's what the question is. What goes in this box? What is the rate? Not deducing the rate equation, that's been done for you. Using the rate equation rather than working it out. Yeah, let's have a look at the next line. 0.02. 0.01. Halving this. 0.025. What will be the effect on the rate in that case? Okay. Right, bit of a trick on this. That, you're going down by half. You're halving your concentration. What effect on the rate? Answer, of course, no effect at all, because it's that H plus doesn't appear in the rate equation, so whatever you do to this H plus does not affect the rate whatsoever. So you go from, that's the same as that to that, that to that, gives you that rate, just the fact that we're going that down. So you look at that line and that line there, halving the rate, no effect. So 2.3 times 10 to the minus 6, no effect, because it's zero order with respect to H plus. It's not in the rate equation. Okay, no effect, unchanged. Okay, let me do another. Let's go to this one. Bit trickier this, asterisk. Get your head around this one. That's easy so far. 0.1. Okay. 0.005. Now, I couldn't care less what I'm putting this in because there's no effect anyway. 0.005. Right. What will be the rate. Work it out now, please, if you can. Okay, so 0.02 to what? To 0.1. That is 5 times greater. And it's first order for hydrogen peroxide. So I would expect the rate on that basis to be 5 times bigger. Okay? So times 5, if you will. However, this one, I'm changing two things simultaneously. This one, I'm halving it, times a half, if you will. So, what will be the new rate? And this is key. You're able to do this. Answer 5 times. I'm noticing I'm going to the first line all the time as my point of reference. I'd advise you doing that. Always go. I mean, it doesn't matter which line you go to, but go to the first line because that's better. So I'd expect the rate 2.3 times 10 to the minus 6. I'm going 5 times faster. It's first order times the rate by 5, and I'm halving it because that down to there, halving it. So times 5 times a half. Two things happening simultaneously. Times 5 times a half is times 5 over 2, or times 2.5, if you will. Right? Okay? In other words, the rate is being affected by both of those changes, and you're going to end up with a rate, if you times that by 2.5, if my maths is right, you end up with 5.75 times 10 to the minus 6. Okay? So that's putting these things together. No problem. Right. Okay, another one. Exactly the same idea. So, it's all about changing two things at the same time and seeing how it affects the whole rate. Now this one can come up, these are, getting onto the high levels here now, so, right, let's have look at a whole different rate equation, which is K equals some stuff called nitrogen monoxide, not interested, but we are interested in the fact it's second order, and something called oxygen, first order. Okay, put a 1 in there if you want. Right, here's the data. Okay, same idea. Nitrogen monoxide concentration, oxygen concentration, nothing else, rate. Okay, be rigorous. Moles dm minus 3. Moles dm minus 3. Moles dm minus 3. Seconds to the minus 1. There's your units right there. Okay, this one will really hopefully nail what I'm on about here. There you go. Right, I'm going to, again, I'm overdoing the questions here. I'm doing it more than what you're going to get in the exam on this, but that means, they will ask the odd one of these, but probably not in this level of depth, but you never know. 0.1. 0.1. Rate 1.8 times 10 to the minus 4. Okay? I'm going to always refer to that top line as my point of reference. It's up to you. I'm going to put a thing around that. I'm always going to try and go back to that if I can. Okay? Doesn't matter how you do it. Right, look at the next line. Okay? So there's a few of these, but it will really hopefully sort it. That's the plan. So the next line, 0.2, 0.1. What's going to be the effect on the rate? Okay, well, 0.2. So 0.1 to 0.2, doubling the concentration. Look at the rate equation. the rate equation. Right, 0.2, doubling that. Okay, it's second order. You double the concentration of that particular reactant, it's second order. You should know it's a squared relationship. The rate is going to be 4 times faster. So, in other words, get your calculator out. 1.8 times 10 to the minus 4 times 4 is 7.2. You check all these, you should be able to deduce this yourself, right? Not just let me rabbit on about it. You should be doing this yourself. 4 times faster as a result of doubling of that. End of. Okay, now let's play with this as much as we can. Next line, 0.3. Again, I'm going to back up to the first line to do my deductions. Okay, 0.1. So, just changing 1 at this stage. That to there, 3 times, I'm tripling the concentration of that, 3 times more. But then, I look at my rate equation, it is second order with respect to that. So if that's 3 times more, this is going to be 9, from the top line, 9 times bigger. Okay, if you times that by 9 and do it and see what I'm saying, watch out, right? Because it's going to be, you just got to watch out for your numbers. If you times that by 9, it ends up as being, if you're going to use standard form, right, 1.62, decimal place a bit, times 10, it's 16. 1.8 times 9 is 16, which means 1.6 times 10 to the minus 3. That, so in other words, that to there, 9 times faster, just like that. Okay? 9 times faster. Second order. Right, another one. Okay, let's tinker around with something else. Let's have 0.1 here. That's good. We'll keep that the same as the first line. And also the oxygen now. 0.1, 0.2. Doubling the concentration of that. What will be the effect on the rate? Okay, well, doubling it. It's first order. You double that, you double the rate. So 1.8, looking at the top line, doubled 3.6 times 10 to the minus 4. Okay, doubling it. I'll put a times 2 in there. So times 2. These arrows are going to get confusing. Whatever. Times 2. No problem. So in fact, easier than the first ones I just showed you. Okay, then let's do another one. Let's have this at 0.3. 18. That at 0.3. So if you compare with the top line, watch this one. I'm tripling that. Okay? But this one, this is a key one. Right? This one, they like these. I'm going to 0.2. So I'm doubling that. I'm doing, in other words, for this line, I'm changing 2 things simultaneously, which will have, if you like, a knock-on effect. So, times 2. Right, what will be the rate? Okay, so that's 3 times bigger. That's twice as big. Answer. Right, what do you think? Okay, that one, you triple the rate, you triple that concentration, you are going to make the rate 9 times faster because it's second order. That one, you're doubling the rate, you're going to double the rate because it's first order, double the concentration, double the rate. So 9 times and twice as fast, first order, 18 times faster. That's how you do it. 18 times faster. So, basically, 1.8 times 10 to the minus 4 times 18, which I reckon comes to 3.24 times 10 to the minus 3. And what matters is, so 3 times bigger, 9 times faster on the rate, twice as bigger, twice as big, so doubling the rate, 9 and doubling, 18 times faster. So times 18, I'm going to write in there. You can see, once these orders get, you've got second order and that, once you start changing two things, you have huge effects on the rate of the reaction. You really push the rate up a heck of a lot. Okay, I got one more here. One more, 0.2, 0.05. What will be the rate there? Again, you should work that out. You stop the video, you work that out for yourself. Okay? So, we go back here and compare with our top line again. Yeah? Doubling it, times 2. Here, 0.1 to 0.05, halving it. Yeah? Halving it. Two things simultaneously. So, what are you going to do? Right? I'll probably write this a bit more. You've got 1.8 times 10 to the minus 4. You double that, 0.1 to 0.2. It's going to be 4 times faster because it's second order. 4. You halve that, okay? It's first order, the rate is going to be half as fast. In other words, times 4 times a half, which is basically the same as times 2. In other words, what you're going to do to that rate there is you're going to times it by 2. Overall, that would be the overall effect of changing those two things simultaneously. Twice as fast. So you're going to end up with that. Okay, quite high level. They like asking that sort of thing. Okay, so be aware on that. Now, I've got a couple more of these as well. I've been quite thorough. What time is it? 22. Let's do one more on this video, and that's your lot. Okay? Take this to its logical conclusion, maybe. Okay, so let's have a beast. Rate is equal to, I'm not going to get involved in other stuff. We're talking, this again is disproportionation. I think you should work out this equation by now. You shouldn't have an issue with it. Iodide, second order. Iodate, I haven't got a charge in there, I think it's -1. First order. H plus. See, this equation is very similar. Work out the overall equation. Water is the other product, but you should be able to sort that. Okay, and you're going to get a product that goes coloured. Okay, sort it. Right, there you go. Second order. So there's a heavy rates equation there. Right. Iodide. Iodate. H plus. Rate. You've got to deduce the rate given the rate equation. Right? It's a hefty old rate equation. Right? I should put the units in, but I'm too much of a rush. Right. 0.015 starting concentration. Initial, always initial rate. Always forget to say that, but it's always initial rate. 0.01, 0.02. Just don't want to mess the maths up. Rate, 4 times 10 to the minus 4. That's the rate. Okay, question says, deduce the rate when the following changes occur. So this one, 0.045. I'll just put the numbers in. 0.01, 0.02. Fill that number in there for me. That's okay. This one, 0.06. You still see that? Yeah. Right, I've got rid of the over thing here, messing me about. Right, this one, hope you can still see it. Yeah, you can, no problem. 0.06, 0.01, 0.04, 0.075, 0.04, 0.1. Okay, let's see whether we can work out. Try and you will find the rate really goes up massively once you start changing all these things at the same time. So I'm going to go to red, I think. Faffing about. Here we go. Times 27. Okay, right. Here, there to there. 3 times bigger. That stays the same. That stays the same. 3 times bigger, iodide, second order. 3 times bigger, that's going to basically do this. That's going to make the rate 9 times bigger. Times 9. You're going to end up with a new rate. You times that by 9, check it, you end up with 3.6 times 10 to the minus 3. Watch again, as I keep saying, your standard, how you write that. Okay? 9 times bigger. Right, let's go this one now. Okay, 1 and 3. Always go perhaps to your first line. You can go to any line, but go to your first line, maybe that's easier. So, 4 times bigger. Okay? Stays the same, thankfully. This one, doubling it, twice as big. What will be the overall effect? Right, we come from here. 4 times increasing that, you're going to make this rate go 16 times bigger. Right? Twice as big, right? Second order, 4 times. So in other words, both of those being second order are going to have an effect on the rate, where the rate is going to be 64 times bigger. One's making it 16, one's making it 4. Overall, the rate 64 times bigger. Okay? So if you times 4, it's going from the top line on these. 4, so 4 times 10 to the minus 4 times by 64, according to my maths, alright, comes to 5 times 10 to the minus 2. Check that. 64. That times 64 comes to that. Of course, I don't appear to have a calculator. I'll give it a whirl. Right. 4 times 10 to the minus 4 times 64 equals 2.56 times 10 to the minus 2. So 64 times bigger. Okay, right, finally, let's go absolutely wild with this last one, 0.075. Okay, so that, by my reckoning, is 5 times bigger. This one, 4 times bigger. This one is going to go bonkers. 5 times bigger from the top line. Right? Always refer to the top line. Always do that. Well, it's up to you, but I do because I'm slow. Right? 5 times bigger. Right? So what's going to be the effect? 4 times 10 to the minus 4 times. That's 5 times bigger. And to make it even worse, it's second order. So it's going to make that reaction 25 times faster by changing that. Changing this one, it's first order, 4 times bigger. The reaction is going to be 4 times faster. There it is. And this one, 0.02 to 0.1, 5 times bigger, and it's second order. That one's going to make it 25 times bigger. So in other words, it's going to make it what? How many times bigger? Times 25 times 4 is 100 times 25 is 2,500. So changing, so I've got written down here, changing that 5 times, second order 25, that one 4 times bigger because it's first order, that one 5 times, 25 times bigger. It's going to make that reaction 25 times 4 is 100. 100 times 25 is 2,500. It's going to make that reaction 2,500 times bigger. Okay? So it gives you some idea. Okay? And that times 2,500 equals, bear with me, I'm losing the plot here, but 4 times 10 minus 4 times 1. Rates 1. You don't have to have tiny numbers for rates. You can have any numbers. Okay? So that tells you how to deduce the rate once you know the rate equation, which you will be given, how changing the concentration of various starting concentration of reactors will affect the rate. Okay? So you've got to sort of cumulatively add them together. Okay? It's not difficult once you get the hang of it.